Electrophiles. So first thing that we'll try to do here is try to identify an electrophile. So electrophiles are basically either sometimes neutral or sometimes positively charged species. Positively charged they can be, so that they are looking for electrons, right? Electron pair, right?
Right.
The key quality of them electrophiles are that they have an empty atomic orbital, or they could also have a low energy anti-bonding orbital. Low energy anti-bonding orbital. So we'll see several cases, at least 5 types of electrophiles we'll see, where either they will have an empty orbital or they will have a low energy anti-bonding orbital, and we'll see how they react. So the book talks about hydrogen cation is the simplest electrophile. Since it is a bare proton, it needs 2 electrons desperately. So it will attach itself to any place where there are 2 electrons. So if there is a lone pair on some nucleophile, it will just attach itself there, right?
Right.
So it will attach itself, and therefore a single bond will be formed where both the electrons in that single bond will come from the lone pair,
Yeah.
right?
Right.
So he talks about how H plus acts with, say, OH minus. H plus acts with OH minus, where there is an extra electron on the O. There are actually 2 pairs on the O. Actually 3 electron pairs, no? So OH minus structure will be like this, right? There will be 3 lone pairs and there will be negative charge here, right?
Yes.
And when there is an H plus, it has nothing, it has no electrons, so it will, these 2
Yeah.
electrons will move out like this here, and that will
Yeah.
make a bond, and the
Right.
resultant would be HO, and now the negative charge will be cancelled with the positive charge, and resultant will be water, right?
Right.
So this is this part acting like a electrophile, and the lone pair on OH minus is acting like a nucleophile. So this is the nucleophile here, right? So
Right.
similarly, the H plus will also react with water, because oxygen, this water still has lone pairs, right? And if there is H plus available, again these can also react with this, and it will become H3O plus. Why does it become H3O plus?
Because it is
Because because overall this was neutral and this was positive, right?
positive. Yeah.
And charge cannot be conserved, cannot be destroyed.
Right.
So finally, it has to have a positive charge, right?
Right.
So that is the hydronium ion. So, so for example, H plus was the simplest electrophile which had an empty orbital, right? Empty 1s orbital.
Yeah.
You
Right.
could also have things like boron hydride, which has empty orbitals again, but it is not 1s orbitals, it is sp2 orbitals, right?
Right.
Actually, it's an empty p orbital, because
Yeah.
when boron hydride is formed, these 3 will be taken up by sp2 hybrid orbitals. And how
One.
does sp2 hybrid orbital get formed? There is one s and 2 p's,
Two.
right? So one p
Yeah.
is remaining, right?
Right.
P is remaining, which is going to be empty, right? So
Yeah.
this empty orbital is also another indication that it is an electrophile, because if there is an empty orbital, it wants it to be filled,
Well, right.
right? And anyway, this boron is electron deficient, right? It's 6 electrons.
Right.
So what will happen is boron trifluoride or aluminum trichloride, similarly, they will also react to form more complicated complexes. So the next page, he gives an example of a reaction, which is diethyl ether. Diethyl ether is something like this. There is an O, there is a lone pair of electrons, then there is another like this. Actually, oxygen has 2 lone pairs, but you are not showing the lone pair that doesn't participate.
Okay.
So basically, he's not drawn the other 2. Okay.
Right.
Actually, because oxygen has to have 8, no? So if it was
Yeah.
just this much, it will be 6 only, right?
Yes.
He's not showing that
I
because
get
it's not participating. Now, BF3 again, BF3, what happens is, now this is having an extra lone pair, so it will obviously be a nucleophile here.
it.
And this lone pair will be donated like this, and a bond gets formed. So it becomes O,
Right.
like this, like this, like this, like this, and a bond BF3. And originally everything was neutral, so this is still neutral. However, you can put this becomes slight positive
Positive and
and
that.
this becomes slight negative, because the two were coming from this side, no?
Yeah.
So technically it has lost
Last one.
both and got only one in the bargain, right?
Yeah.
So it has lost one electron overall, right?
Right.
So he's saying then that few organic compounds have vacant atomic orbitals, right?
Right.
Few organic compounds have vacant atomic orbitals, because mostly organic compounds will have 4 bonds everywhere. No, it will not be like they will have empty orbitals like
Right.
BF3 and BH3, right? These are examples of compounds that have empty orbitals, empty p orbitals, right?
Right.
However, this is unlikely to happen when you have carbon compounds.
Carbon. Yeah.
It will be every time it will be 4 bonds, right?
Yeah.
So in most organic electrophiles, the LUMOs, or the lowest unoccupied molecular orbitals, are instead low energy anti-bonding orbitals associated with electronegative atoms. So what is he saying here? He's saying most organic electrophiles will be will have low energy anti-bonding orbitals, or LUMOs, orbitals, which will be the LUMO, lowest unoccupied molecular orbital, right? Which
Right.
are attached to an electronegative atom, which are associated with an electronegative atom. So what does this mean? What it means is, see, think about the carbonyl group. Okay,
Right.
carbonyl group looks like this. Fine.
Mm.
So right now, if you look at the carbon, it has 4 bonds. No,
Yes.
so it doesn't have some empty orbital lying around which will accept electrons, right?
Right.
But that carbon is still electrophilic. It is still electrophilic because what happens is that this oxygen is taking away slight electron density, right? It will become slightly negative and this will be slightly positive, right?
Right.
And this carbon, the way it forms the bond is, here the hybridization of carbon is what? sp2, right?
Yes.
So 3 sigma bonds are there, 3 sigma bonds, 1 sigma bond here, 1 sigma bond here, and one of these is sigma bond, right?
Yes.
And one p orbital that was not used in hybridization has formed the pi bond, right?
Yeah.
One p orbital is involved in a pi bond, right? So there
Right.
is one pi bond here, one sigma bond here, right? Now, when you make the structure, the molecular orbital structure, right? You generally, if you remember, the way we drew molecular orbital structures, we took 1s1, 1s1 and made bonding and anti-bonding, right?
Yeah.
Correct. However, here what is happening is you have carbon and oxygen, they have different energies, right? They have different energies.
Yes.
So the molecular orbital structure will be slightly different because they will have two different types of atoms are combining, right?
Yes.
So there will be basically orbitals can be formed from 2s and 2p from both 2s and 2p from carbon and oxygen, right?
Right.
Correct. Now 2s part we can sort of ignore, but the 2p of carbon and the 2p of oxygen are combining, right?
Right.
The 2p of carbon, there are 3 orbitals like that, right?
Yeah.
And similarly there are 3 orbitals of oxygen. However, oxygen is lower in energy, lower energy. Why is oxygen lower in energy? So think about it. There is 2p of carbon, and carbon has 2p2, right?
Yeah.
1s2, 2s2, 2p2 for carbon.
Yes.
And for oxygen, it will be 1s2, 2s2, 2p4, right?
Right.
It will be like this, right? This is oxygen. and I have drawn it slightly lower in energy. Why did I do that? Because first of all, it doesn't have to be equal energy because they are not identical atoms, right?
Right.
So I have to decide whether carbon is higher energy or oxygen is higher energy, right?
Right.
Which orbitals are higher in energy, oxygen's 2p or carbon's 2p? Now, the way that decision is made is that if you go in the same row of the period, right? Like, or carbon is somewhere
Yeah.
here, oxygen is here, right?
Yeah.
So if you go in the same row, what is the happening to the size of the atoms? Size of atoms?
They decrease.
Size of atoms is decreasing. So each orbital of oxygen is closer to the nucleus, right?
Right.
Orbital closer to nucleus. So if it is closer to nucleus, it will be more stable, no? Because orbitals have then electrons, and electrons closer to the nucleus will be more tightly held, right?
Right.
Makes sense.
Yeah.
It will be more stable, and the farther you are here, the orbitals will be farther away from the nucleus, so higher energy, right?
Yeah.
So carbon has higher energy 2p and oxygen has lower energy 2p, right?
Right.
Now these electrons can the two p's, right? They can form pp sigma bonds or pp pi bonds, right? See,
Right.
p orbitals are like this, and they can do a head-on thing, right? Or
Yeah.
they can do a side-on thing, right?
Upside on. Yeah.
So these are the two types of bonds that can form, right? So
Right.
if 6 atomic orbitals combine, there will be 6 molecular orbitals, right?
Yeah.
Correct. So
Yeah.
what we will draw, the way we'll draw is we'll draw a sigma, which is a end on or head on molecular orbital that is formed, bonding. And then we will draw two side on ones, right? These are the pi bonds, okay? These
Right.
are pi bonds, 1 sigma, 2 pi, and then there is a pi star, pi star, pi star, and then there is a sigma star,
Master.
correct?
Right.
My uh, diagram is a little wrong in the sense that my energy levels should be a little higher. So I will put sigma star, sigma here. I will put pi 2 orbitals, molecular orbitals these are. Then I will put pi star here, right? And I'll put sigma star here. Okay.
Okay.
Now I will start filling up. Now I'll start filling it up. So I have 1, 2, 3, 4, 5, 6, right?
Yeah.
5, 6 are there. So I'll put like this. Correct.
Correct.
Actually, this is not going to be the case because the carbon already used some things to form the other bond. No, so C double, there is some p orbitals are used in sigma with other atoms, right?
Right.
Right. Oxygen, on the other hand, has nothing to do. Like here, the availability of uh, p orbitals is not two. The p electrons is not two.
Two
So
is also not. Yeah.
so one of them will be used up elsewhere. So in general, what I want you to see is that uh, I don't care about the numbers here right now. What I care about is this orbital is higher, this orbital is lower in energy, right? And
Right.
finally, these are the bonding MOs, and these are the anti-bonding MOs, right?
Right.
So once bonding and anti-bonding MOs are decided, now you can notice one thing, that the bonding MOs are closer to this, right? The
Right.
oxygen contributes more to the bonding, right?
Bonding. Yeah.
And carbon contributes less to the bonding
Bonding.
because it is higher energy. And carbon is closer to the anti-bonding, right?
Right.
Carbon atomic orbitals are closer to the anti-bonding, right? That that tells you also the fact that more of the electrons which are involved in bonding will be towards the carbon or towards the oxygen. Like
Okay.
actually, the bonding electrons are forming the bond. No? The electrons which are in bonding MOs, right? Now, if they are closer to oxygen in energy, then they will spend more time towards the oxygen, right?
Yeah.
Anti-bonding MO does not contribute to bonding. So all the bonding electrons are closer in energy levels to the oxygen atomic orbital. So therefore, they will be contributing, or they will be towards oxygen more of the time than towards carbon. So that also explains why this is electronegative and this is electropositive, right?
Yeah.
Also, now we know what he's saying here. The low energy anti-bonding orbitals associated with electronegative atoms. So these are the low energy anti-bonding MOs that are empty. These are the anti-bonding molecular orbitals that are empty right now, right?
Yeah.
So what happens is, when an electrophile, when a nucleophile comes, right? Uh, Nucleophile has an abundance of electrons, and those electrons want to go somewhere where it can occupy a low energy orbital, right? So the
Right.
only low energy orbitals available in this case will be the anti-bonding MOs, right? It's not like carbon has an other empty orbital hanging around, right?
Right.
It can only go in these anti-bonding MOs. And one thing that you have to understand here is, as soon as carbon goes into the anti-bonding MO, right? As soon as some electron goes into the anti-bonding MO, then one bond has to break, no?
Yeah.
If a lone pair of electrons comes here, right? Then this bond is cancelled, no? This energy that was reduced is now increased again, right?
Right.
Why does a bond break? If you think of helium, right? Helium, it had one s2 here and one s2 here, and there was a bonding sigma that was fully occupied, and there was anti-bonding also fully occupied, right?
Uh,
Right. So
yeah.
what is happening in helium? The reason that helium 2 doesn't exist is because there were 2 in bonding and 2 in anti-bonding, right? So
Yeah.
whatever gain was there, or whatever energy was reduced here, is cancelled here, right?
Right.
In hydrogen, both were here, but nothing was here, right? So H2 exists, correct?
Correct.
So if suppose you have some situation where there are some bonding MOs that are fully filled, like in the bond that we are talking about, carbon double bond, right now carbon has formed its full complement of bonds, right? All the bonds that it needed to form, it has formed, right? So
Yeah.
all the bonding MOs will be fully filled, right? Correct. But anti-bonding ones will be empty, right? Anti-bonding ones will be empty right now for carbon. Okay. So if an electron is coming from some nucleophile, right? Some nucleophile has a lone pair of electrons, right? And if it attacks this carbon like this, right?
Yeah.
Then it has no space to go in the bonding place, right? It has to go here, right? Correct.
Yes. Yeah.
If it goes here, then it will cancel out one bond, no, like this.
Yeah.
Just like helium, if you
It
put,
will cancel.
it will cancel out one bond. So if it comes here, what has to happen is the 2 electrons will form a new bond here, right, with the nucleophile. So you'll have carbon, there will be a nucleophile bond because of the 2 electrons donated, right?
Yeah.
And the double bond or the pi bond has to break, and it will become a single bond. And where will that pi bond go? It will go on the atom only, the 2 electrons
Right.
from the pi bond, right? So
Yeah.
it will eventually become C nucleophile and O minus, something like this. Instead of being like this, right? This pi
Right.
bond has to come here, and the electron pair had come here, right, to form a bond.
Right.
So that is what will happen. So what is he saying here? He's saying uh, the antibonding orbitals can either be pi star orbitals, pi antibonding orbitals, or sigma star orbitals, So these are the antibonding orbitals where an electron pair will come from some nucleophile, right? Correct.
Right.
In other words, molecules which make good electrophiles might have a double bond or a single bond to an electronegative atom. Why an electronegative atom? Because then only you will get the dipole plus, right? If there
Right.
is a electronegative atom attached here, then only you have a tiny plus here and tiny minus here, which attracts the nucleophile, right?
Right.
So as long as you have a double bond or a single bond to some electronegative atom, what will happen is you automatically are a good target for any nucleophile, right?
Right.
Correct. So then he's saying the most important molecules with a double bond to an electronegative atom are carbonyl compounds. So this is very important. So here he's saying the low energy pi star orbital is available to accept electrons. So that is what we are talking about. The lowest energy, lowest unoccupied molecular orbital is a pi star orbital, because the pi bond here is the weakest bond, right? So think about it. If you have a molecular orbital chart, the sigma bond is stronger, no? So it will be lower, right? The stronger bond will be
Right.
lower in the sequence, no?
Yes.
And the pi bond will be slightly upper because pi bonds are weaker, right? So if pi bonds are here, the anti-bonding pi's will be here, pi star, right? So, and sigma star will be here, right? So,
Yeah.
so this might be filled. These might be filled. That means these bonds are made, right? But these are two pi bonds, for example, right? So now the lowest unoccupied molecular orbital will be this pi star. That is what he's saying. Okay. The low energy pi star orbital is available to accept electrons, and its electrophilicity is further enhanced by the partial positive charge at carbon, which arises from the CO dipole. So there is a partial positive charge on carbon, and that further makes it susceptible to accept electrons, right? So now look at what he has done here on the next page. Boron hydride, BH4 minus, right? Boron hydride anion is acting like a nucleophile. Why is this a nucleophile? Because obviously right now it has formed all the bonds. However, there is an extra, it has formed all the bonds and there is a negative charge here, right? So
Yeah.
since it is negatively charged, automatically it gets attracted to any positive dipole, right? Positive end anywhere.
Right.
So notice that this is slightly different from the cases that we have so far encountered. In the other cases that we encountered, there was a lone pair of electrons which was already available, right? Correct. So, for example, uh, when H plus bonded with OH minus, right? O had many lone pairs, no?
Yeah.
So the lone pairs were available to be transferred, right?
Yes.
So this was the nucleophile here, correct?
Right.
However, if this is acting like a nucleophile, what is happening? Is there any lone pair right now? No.
No.
If you realize BH3 was electron deficient, no?
Yes.
So if you put BH4 minus, that means
Right.
you have found 4 bonds, right? But B doesn't
Yeah.
have any electrons, right?
Right.
So there is no lone pair available. The reason for its nucleophilicity is basically the fact that it is negatively charged, right?
First. Right.
And it will try to go towards this positively partial positive charge, right? Towards the carbon, right?
Right.
So now how will it go towards that carbon? It doesn't have any electrons to donate right now immediately. So what it does actually is this bond has the 2 electrons, right? This bond itself donates like electrons to this anti-bonding orbital here. Okay. The anti-bonding pi star orbital it comes to. This carbon will have a pi star because of this pi, right?
Yeah.
There is a C double bond O here. So one double bond is a pi bond, and that pi bond right now is occupied, but its anti-bonding MO is unoccupied, right? So this electron will go to that pi star. So therefore, this bond has to break now, right? Correct.
Yeah.
So what you will end up having is this bond has broken and hydrogen has come here, right? Formed a bond with this, right? So,
Yeah.
so what has technically happened is both the electrons of this bond have been taken with the hydrogen and gone here, right?
Yeah.
Correct. So if hydrogen takes both the electrons from the bond, the remaining molecule will become neutral, right? Because you understand why?
Yeah. I got it.
Right. So because it was sharing one, right? And it took both and went, right?
Meant. Yeah.
So it will become CH, and these two are regular bonds that are already there, and this becomes O, and O becomes a minus, right? Because this electron came here, right? Because as soon as C formed a sigma bond with hydrogen, these electrons, right? Then one bond has to break, right? The pi bond has to break because
Right.
that came in the pi star antibonding, right?
Right.
So finally, this product is formed. Pi bond is broken, but sigma bond remains. So the sigma CO bond remains because that is more strong than the pi bond. More strong, and it is more stable or lower in energy, right?
Energy. Yeah.
So the lower the energy of the sigma bond, the higher the energy of the sigma star. Okay. So
Right.
the electron that is coming in will not go to higher energy antibonding. It will try to go to lower energy antibonding, right? So it will go to pi star
Yes.
instead because pi star is more easily gettable, right?
Yeah.
You understand? So now he's saying
Right.
since the reaction is putting electrons into an antibonding orbital, a bond has to break. The breaking bond is the C double bond O pi bond. The sigma bond remains intact. The electrons in the bond have to go somewhere and they end up as an extra lone pair on oxygen, right?
Right.
The product has a new CH sigma bond in place of the C double bond O pi bond, right? So
Yeah.
there are other examples, there are other cases where what happens is molecules with a single bond to an electronegative atom. So far we are looking at pi bonds that were donating electrons, right? Pi bonds that were breaking, right? So now we look at molecules with sigma bonds, sigma or single bonds to electronegative atoms,
Right.
electronegative atoms. So for example, the molecule that he will take is say HCl or CH3Br. Okay. Now, what happens is obviously there is a carbon bromine bond here, no?
Yeah.
However, this is a not so strong bond because there is an electronegative difference, right?
Yes.
There is a tiny dipole here. So this sigma bond is susceptible to breaking because anyway the bond is a little polarized, right?
Right.
So if a nucleophile comes, with an electron pair, right? So
Yeah.
so what will happen is this electron pair can attack the carbon and form a bond like this. But in the process of forming a bond, it will have to go to the sigma star antibonding MO, right?
Right.
Because carbon here has formed sigma bonds with everyone, right?
Yes.
Correct. So there are
Correct.
4 sigma bonds right now. So all the sigma bonding MOs are occupied, right? All the sigma bonding MOs for carbon are occupied.
Occupied. Yeah.
So only the empty sigma star it can go to, right? And it will go to the lowest energy antibonding sigma star, right?
Right.
So the lowest energy antibonding sigma star will be the one corresponding to the least strong sigma bond, right?
Right.
Like there are 4 sigma bonds competing, no? This bond, this bond, this bond, this bond, right? Now, which sigma bond has the lowest energy? CBr, right?
Yeah.
Not lowest energy, it has the highest energy, right? Because it will be like this. There will be sigma, sigma, sigmas. There will be 3 sigmas at the same level. These are CH sigma bonds, and there will be one sigma, which is the CBr sigma bond, right?
Yes.
You understand?
Yeah.
Because this is high electronegativity difference, no? So also bromine is much larger. So overlap is not so good, right? Between
Yeah.
carbon and
But
bromine, right? So
yeah.
since it is least stable bond, its sigma star is also more accessible. It is not so far. This one will be high value of sigma stars, right?
Right.
So the electrons that are coming will go and occupy this sigma star, and that means that this bond has to break, no, the CBr now,
Yeah.
correct?
Yeah.
So if electrons go into the anti-bonding MO corresponding to your bonding MO, then that bond has to break, right? So what happens is then CH, H, H, nucleophile, and this bond breaks and comes here, and you get a bromine ion, Br minus. Okay. So that is what he is showing also in the ammonia case. In the below there is an ammonia case also,
Yeah.
right?
Right.
So in the box he has written, see, we you may recognize this reaction, the NH3 plus HCl reaction, as a reaction between a base and an acid. So he's saying all acid base reactions are reactions between a nucleophile, which is the base, because nucleophile is generally negatively charged, base is the one which is negatively charged, right? And an electrophile, which is an acid, right? We
Yeah.
call, so basically Lewis acid, Lewis bases are an alternative way of talking about electrophiles and nucleophiles, right? So we call an electrophile an acid if it has an XH bond, X being any atom that loses H plus in its reactions. So if an acid loses H plus, now H plus is obviously a electrophile, right? Correct.
Right.
So,
Right.
so if a molecule is losing H plus, then that is an acid. This acid is behaving like an electrophile. And a nucleophile is a base when it has a lone pair that it can donate to the XH bond, right? So we have already discussed the Lewis acid base concept. So later we'll come back to it again. So now he's talking about, so far what have we seen? So far we saw that any molecule which has a bond to a carbon with an electronegative atom, whether it is sigma bond or pi bond, right? It is susceptible and it will become an electrophile, right?
Yeah.
So far all the electrophiles you were seeing were molecules that, okay, I'll just list it out. Uh, First type of electrophile, it says empty orbital, right? Empty orbital type of electrophile was H plus, BH3, right? Then we saw uh, carbon bonded to an electronegative atom, right?
Right.
Carbon bonded to electronegative atom, even if it is like this. Single bond also it could be double bond also. Here it is pi bond, here it is sigma bond, right? And these carbons are susceptible to be electrophiles, right? Because the bond can be broken, this one, right? Now he's talking about the third type he's talking about here is some sigma bonds are electrophilic even when they have no dipole. Here at least there was a dipole, no? Right?
Right. Yeah.
So sometimes there is no dipole and still it is susceptible. How? So for example, he's saying Br. Bromine is strongly electrophilic because it has a weak sigma bond, very weak sigma bond. Why is it having a weak sigma bond? Because there is a low energy sigma star orbital, and he's asking again, why is sigma star bond orbital low in energy? Well, because it is slightly electronegative, but it is also large. It has to use 4s and 4p orbitals, right, to form its bonds, right? Now, these orbitals are super large and they are very diffuse, right? So, because they
Yeah.
are very big, now the overlap will never be very strong, right? So, they overlap poorly, meaning the sigma star molecular orbital is not raised far in energy and can easily accept electrons. What is he saying? When Br and Br combine, the orbitals are 4s and 4p and all, right?
Yeah.
4s, 4p, and so on. So, generally when two orbitals overlap you get a big drop in energy for the bonding MOs, right? And a similar big high energy anti-bonding MOs generally, but that is if there is a strong overlap, right? In this case you don't get a strong bond, you get only this much, and therefore the anti-bonding is only here only, right?
Right.
You understand? So the bond is weak, therefore the anti-bonding is low in energy. And if there is a strong nucleophile, right, anything that has a pair of electrons that it wants to donate, it will easily be able to give it to this, right? This one will be filled, but this one will be empty, right? So this will become your LUMO. and the
Correct.
nucleophile will easily be able to donate this because the height of this barrier is not high, it is low energy, right? So as soon as it does that, the Br bond has to break. If this became occupied, Br has to break, right? Correct.
Right.
So he's saying how different the situation is with a CC bond. CC single bonds, on the other hand, are very strong because these are tiny orbitals, 2s and 2p and all. No? The
Yeah.
orbitals that overlap here are 2s and
And
2p, and they
2p.
are correspondingly much better overlap. Okay, so the bonds are much stronger. So that is what he's explaining on the next page. If you see the top diagram, right? So Br when they combine, the sigma orbital is very low energy gain, right? Small energy gain or weak
Okay.
bond is
Yeah.
formed. So the low energy LUMO is easy to put electrons into, right? On the other
Right.
hand, CC bond, there is a big gap. CC sigma orbital is much lower in energy, right? Okay. Now,
Um.
uh, look at the tiny box on the left. He's saying the unreactivity of CC bonds is why we think of structures in terms of a hydrocarbon skeleton and functional groups. Now, because CC bonds are strong, therefore it is very hard to tamper with the overall CC structure of a molecule, right? Like overall the CCCCC, that long chain structure, it is hard to tamper with that. That doesn't
Yeah.
affect
Yeah.
very easily, right? So that is why in organic you think of CCCC structure as the base structure and some functional groups which are the more reactive parts, right? So for example, he is now given some examples of how bromine reacts as an electrophile. So he has taken this methyl sulfate, right? Methyl sulfide. So methyl is actually CH3. Okay. So methyl sulfide, it has a lone pair here. Actually, sulfur has two lone pairs, but you are not showing the other one. Other one is here hidden, right? So now if there is plus Br2, now obviously this lone pair can be donated, right? So this lone pair will come to here and it will take the sigma star antibonding molecular orbital here, right?
Yeah.
And form a bond with this. And because it has formed a bond, this bond must break. So what you will get end is Me S Br Me plus Br minus, right?
Right.
Now notice that originally compounds were neutral, no? And you are getting a Br minus, so you should have a Bs plus here, right?
Yes.
Why a plus? Because plus plus minus should be there, no? It should
Either.
be
Right.
neutral. And
Yeah.
also you can think of sulfur gave away both the electrons and got back only one, right? In the single bond. Got only one, no?
Yeah.
It gave away both the electrons to
Got
form the
got only
bond.
one.
Yeah, so it is having a tiny positive, right? So now he has listed down the different ways in which electrophiles can accept electrons into empty low energy orbitals. So first case was positive charge, which represents an empty orbital, hydrogen, right? Hydrogen ion. The second case was neutral molecule like BF3. Third case was double bond with an electronegative element, right? And fourth case was single bond to an electronegative element. And the fifth case that he has mentioned here is large atoms making single bonds which are weak, right?
Yeah.
That doesn't have an electronegative element necessarily because there's no dipole here, no dipole, right? So actually 5 types of electrophiles he has identified, right? You understand?
Yeah. I got it.
Okay, so now we're looking at how to write mechanisms for reaction. So quickly we will go through that, then we'll go to the next chapter. So mechanism for reaction is written by using the method of curly arrows. So the curly arrows is going to show the movement of a pair of electrons. Movement of a pair of electrons. Now this pair of electrons will move from where will it move? From a filled orbital to an empty orbital, right? To an empty orbital. So that is what this arrow will signify. Okay. Now, this movement, the result of this movement will be what? It will form a bond, right? It will form a bond between nucleophile and electrophile. Nucleophile. So far, we have already been using this. So we are just summarizing this so that we are clear on how to write the mechanism of any reaction, right? You can see those examples that are there. We have already discussed, so I'll not go through that again. The two examples that are there, right? Diethyl ether and hydroxide ion, right? Correct.
Right.
So now, a curly arrow always represents two electrons, right? Two electrons because it takes two electrons to fill an orbital, right? And form a bond.
Right.
So, so there are special reactions where there is only one electron being transferred. Those are called radical reactions, which we will see much later. Right now, you should just remember that curly arrow means two electrons are moving, right? Correct.
Correct.
Now, sometimes, obviously, you have to draw another curly arrow to denote, curly arrows could also denote bond breaking sometimes, right? So, for example, in the Br case, we drew a curly arrow from Br. This arrow has to go back here, right?
Right.
And nucleophile, this came here. This formed a bond and this broke a bond, right? So,
Right.
so it has moved from a bonding molecular orbital to a lone pair, right?
Right.
It's gone to a lone pair type of situation, right? So, okay, so these are basic things that we need to know. Now, he next page he's mentioning that charge is conserved in each step of a reaction. If the starting materials have no overall charge, then the products also cannot have any overall charge, right?
Right.
Correct. Uh, then specifically he's mentioning some points like uh, when a pi bond is broken, when a pi bond is broken rather than a sigma bond, only sigma bond will be left in place. Okay, that is obvious. We already know that. So uh, this section is fairly straightforward. Uh, so he's talking about now pi bonds as nucleophiles, and then he will talk about sigma bond as nucleophiles. Sigma bonds as nucleophiles. So what does that mean? Pi bond as nucleophile. Nucleophile means it is donating some electrons, right? Because it is attracted to the nucleus. It has more negative charge, right? So example that he gives is the alkene example. So suppose this is the structure. So that means there is a carbon here and there is a carbon here, right?
Right.
And there is HH which are not shown in this. So if you have plus HBr, right? Correct.
Correct.
So this pi bond, the pi bond in the alkene double bond, right? It
Yeah.
can donate electrons. It can donate electrons to the H plus, right? So this
Yeah.
HBr is an acid, and H it breaks down as H plus
Awesome.
and
Yeah.
Br
Right.
minus, right?
Right.
This pi bond can donate electrons to this and form a bond with that, right?
Right.
So what will happen is C will form a bond with H, and since it donated both of its electrons, it will end up with a positive charge, right?
Right.
Correct. And the pi bond has broken, and there is this structure has come, right?
Yeah.
And there is a plus Br minus, right?
Yeah.
Now think of the Br minus. Uh, wait, 1 second. Okay, so H plus has not bonded with this. So what has happened is H plus has come to the other carbon. Why? Because see, he has drawn the structure like this, double bond like this, plus HBr, and he's saying that this bond is coming like this, and the carbon this becomes, there is a carbon here and there is a carbon here, and this attaches with this. And this carbon ends up having a plus because it
Understand.
lost both of its electrons, right?
Yeah.
And this carbon still retains one here, right?
Right.
For this carbon, there is no problem. No, it gave away the one from here and but got back a one here, right?
Yes.
And then there is a Br minus, and this Br minus comes and attacks here, right? Because negative will be attracted to this positive,
Positive.
and
Yeah.
you'll end up getting a Cbr and CH, something like this, right? So here the pi bond is acting like a nucleophile. Why is the pi bond acting like a nucleophile? Because obviously it has electron density which can be donated, and uh, H plus is definitely looking for electrons. It is a very strong electrophile, right?
Right.
So, uh, so he's saying when the nucleophile is a pi or a sigma bond rather than a lone pair or a charge, there is always the question of which end of the bond actually reacts. So you understand, right now we had that doubt, right? Like which one will get the positive charge and which end will react, right?
Right.
So there's always that question. We will understand that much better when we do alkenes. When we discuss alkenes in general functional groups, then we'll realize ki whether H will come on this or H will come on this. Obviously, that is a question that could be asked, right? Like if you add HBr, right? Will H come on this carbon or will H come on this carbon, right? There is an
Right.
ambiguity, right?
Yeah.
So that part we will understand how it happens. However, for now, what you need to know is what is happening. Pi electrons are breaking and going to the edge, forming a bond with this sigma bond. And
Right.
later the Br minus comes and attaches itself to this plus charge, right?
Right.
The other case was the BH4 minus case that we had already seen, right? So I will
Yeah.
let you read through that. Now, drawing your mechanisms with curly arrows, that section he talks about couple of things which are important. So whenever you are trying to predict what will happen in a reaction, these are the important things. Identify which bonds are broken, identify bonds that are broken and bonds that are formed, bonds broken and bonds formed. And the most important thing is identify which one is electrophile, which one is nucleophile. Correct?
You're right.
So which one is nucleophile or electrophile? So he gives three examples. We will do two of them. So let's do the first one. He's saying methyl iodide plus PH3P. This is, right now you don't know what PH3 is. PH3 is actually a phenol group. Later we'll see what the structure of PH3 is. Methyl is CH3, right?
Yeah.
Gives PH3P plus Me plus I minus, right? So let's think about what should happen in this reaction, right? So we know that this is a single bond between a carbon and an electronegative atom, right?
Right.
So here there is a sigma bond with a carbon and an electronegative atom. So the carbon is slightly positive, right?
Right.
So it will be an electrophile, right? Carbon is an electrophile here because it is slightly positive, right?
Correct.
Correct.
Yeah.
So also if you think of the phosphorus here, right? Phosphorus is like nitrogen. It will have a lone pair of electrons here somehow because these are single bonds, right? Just like nitrogen and NH3 if it was, right? NH3 has a single bond with HHH, right?
Right.
So phosphorus will definitely have a lone pair of electrons, no?
Correct.
Because there will be single bonds here with this 3, and there is a lone pair that is pending, right? That is that's not occupied right now, right?
Right.
So this is definitely a nucleophile, correct?
Correct.
You understand the identification is important.
Yeah.
CH3I, this is the electrophile, this is the
Yeah.
nucleophile.
Yeah.
So now these two electrons will come and attach themselves to the carbon, right?
Carbon. Right.
And they will form with the carbon, they will form a bond, right?
Right.
Since phosphorus has lost both the electrons, it occupies a plus charge, right?
Right.
Now, these electrons went to the sigma star bonding, anti-bonding orbital, right?
Yeah.
Because there was already a single bond, sigma bond with the iodide, right? So they
Right.
went to the sigma star. So the iodine bond must break, and I will take away the electrons here and take it with I minus, right? So
Right.
notice that charge is conserved in the whole process, right? So that is what is happening. He is also talked about, see, a wrong mechanism would be what? Wrong mechanism would be you don't break the bond with iodine. Why is it wrong? Because carbon now has 5 bonds. You understand?
Yeah.
Like if you are making a new bond with the carbon and the phosphorus, right? One bond has to break, right? Because that sigma star is occupied, then it has to break the Ci bond, right?
Right.
Are you understanding what is happening?
Yep.
Okay. Mechanisms with several steps. So let's look at this one. There is an aldehyde. This compound is called an aldehyde. This one. So actual structure of this is CH3, CH2, C double bond O H.
OH.
Okay. And now you are adding sodium cyanide and water. Now sodium cyanide is a solid, but when NaCN you add, it becomes Na plus and Cn minus, right?
Right.
Now Na plus is super stable. There's nothing Na plus does much, right? Cn minus on the other hand has this structure, right?
Yeah.
Something like this. So let's count the electrons. Let's draw the VSEPR structure for Cn minus. So what happens? Carbon has 4, nitrogen has 5. So 4, 5, 9 plus 1, 10, right? 10
Right.
electrons. 6 electrons are used up here. So 4 electrons are left, right?
Correct.
So I will give 2 here and 2 here.
Yeah.
So that will satisfy both the things octets, right?
Right.
And this is the structure of my Cn minus, right?
Right.
Now in Cn minus, which one? It is negatively charged, so obviously it will be a nucleophile, right?
Yeah.
It has to be a nucleophile, no?
Nucleophile. Yeah.
Right? So it has to be a nucleophile, so it is going to donate electrons, right? Somehow it is going to donate some electrons from somewhere, right? So the one which will have the negative end will donate electrons, no? Negative end of this charge will be more spread towards the nitrogen, no?
Yes.
Because nitrogen is much more electronegative than carbon.
And carbon. Yeah.
So charge will be towards the nitrogen. So a negative end should be attracted to the electrophile, right? Since
Yes.
this is a nucleophile. So what we will be worried about is this electron pair, right?
Right.
This electron pair is what will do the thing. Now, if you think of this molecule, here the carbon is slightly positive and is attached with a double bond to oxygen, right?
Right.
So that is already we have discussed that this is a typical electrophile where the pi bond generally breaks, right?
Yeah.
This carbon is a tiny positive, so it will bond with the Cn minus, so you'll get this C and there will be a Cn, right?
Right.
This bond has been formed because these two electrons have come from there, right?
There. Yeah.
And this carbon has to now give away this bond has to break, no? It has to
Yeah.
be
One
become
fiber.
like this.
Yeah.
And this is the situation now. However, this is not the end. Right now, you have come to this state. Now, this O minus and all, it can actually react with water, I think, right?
Yeah.
It can react with water because will it react with water or with something else? It should react with O minus is what? Negatively charged, so it is a nucleophile, right?
Right.
Nucleophile. And water has, okay, O minus end. So, yeah, so it wants a proton somewhere, right?
Right.
So what can happen basically is water structure is like this, and this is positive end, no?
Yes.
these are the hydrogens are positive and there is a negative here. So what can happen is the O minus can form a bond with this, right?
Yes.
And as soon as it forms a bond, it becomes like this, CCN and OH, right? And H, right? And plus OH minus. Because once it formed a bond, this hydrogen has to break apart, right?
Yeah.
Because it got electrons from here, no? So it will give away these electrons, no?
Right.
Right? Because otherwise, what will happen? Otherwise, hydrogen will have more than two. Right?
Yeah.
That is not possible. It doesn't have
Possible.
orbitals, right?
Right.
So finally, you get this OHCN added to the C atom, right?
Right.
OHCN has been added to the same carbon C, and OH minus has come out, right?
Yes.
Correct.
Yeah.
So this is the mechanism of this one. You can read the rest, the next one page and all you can read. It's just two other examples he's telling you. Okay.
Right.
So just go through it once. What we will start next is nucleophilic addition. So basically the point that he has been making so far is uh, we are going to discuss reaction types, and the reaction type that we are going to focus for now is nucleophiles and electrophiles, right?
Right.
And the most important functional group that he has identified is the C double bond O group. This group, either this can either be present in a ketone when there is a C and a C here, or it can be present as an aldehyde when there is a H here and a whatever C here,
Yeah.
aldehyde or ketone. So these are the compounds that, because we know that this is slightly positive, this is slightly positive, these are already electrophiles, right? So what we'll be studying, and the first major reaction type that we'll be studying, is nucleophiles being added to this electrophile, right?
Yes.
Nucleophilic addition to the C double bond O bond, right?
Right.
So we will take a variety of different nucleophiles and they will keep getting added to this electrophilic double bond, right?
Right.
And that is actually a pretty important reaction in the study that we have to undertake. So around 10-12 pages, and it is going to first explain, the first couple of pages he explains how the reaction happens, which we sort of already know, but he will draw nicely all the orbitals and all in the first couple of pages and show you. And then he will take different cases, so different nucleophiles he will take, and he will start showing you how the reactions happen. So the mechanism for the reaction. So the way you are supposed to study now is make notes, in the sense that right now first thing that we are studying is nucleophilic addition. Nucleophilic addition you are studying. So make notes of, first of all, how the mechanism is,
Right.
mechanism, how it happens, and the 5-6 different reactions that we'll encounter. So there are 10-12 pages in the chapters, chapter 6, and there are 5-6-7 different types of reactions that happen. So each of the reactions, how it happens, what are the products, and anyway the mechanism, right? So you should have a good notes where you see all the steps in each reaction, all the steps in each reaction and final products that come. And if there is any name for it, right, it might be called something. So you should be able to now identify nucleophilic addition when it happens. That is the point of the next chapter. Okay.
Right. Okay.
So go through it once. So next week we will finish this. We'll finish nucleophilic addition next week. Okay.
Right.
Which is chapter number 6. Uh, that will cover the aldehyde ketone parts substantially for you. So, okay, we'll continue from here. Just read up chapter 6 now, okay? It should be fairly understandable.
Okay.
Okay. Read up chapter 6, make notes, we'll discuss this in the next class. Till page
Okay.
140.
Right.
Okay. Okay. That's all for now.
Thank you.
Bye.
Bye.